Okay, so what I'm going to talk about today to begin with is something called Wigner's theorem. Now, this
Sir,
is
your
something,
screen
yeah.
isn't visible.
Oh, right. Okay. I was not showing my screen until right this moment, but now I will have to. Wait a minute. Okay, so the first thing we are going to talk about is a very important theorem in the use of symmetries in quantum mechanics. After all, most of the symmetry principles that we are going to discuss are applied in quantum mechanics, although frankly, classical mechanics has its fair share of usage of symmetry principles. Symmetry and specifically group theory became really important in physics via quantum mechanics. And essentially via this particular result, which is called Wigner's theorem. And the theorem essentially goes this way. Any symmetry transformation can be represented on the Hilbert space of physical states by an operator that is either unitary or anti-unitary. Now, let me point out one thing. Many of you may have already heard of this, at least if not heard of this as a theorem, may have definitely seen this used. Especially in quantum mechanics, we use it all the time. Even last semester or last year, actually, we used the rotation operator, for example, as a unitary operator which acted on the space of states. But what is important is the can be here has been underlined. Sometimes, especially quantum mechanics books tend to sort of say that you always have a unitary operator which implements a symmetry. If you're talking of symmetry of quantum mechanics. First of all, Wigner's theorem says not only unitary, you can also have anti-unitary representations. We are going to talk about that as the proof of this progresses. But more importantly, can be is very important. The point really is that when you talk of a transformation in a quantum mechanical system, what changes yeah, what represents the state in quantum mechanics? That's a question for you. Tell me.
Wave function.
Wave function.
What was
Well,
the
wave
question
function
again?
is a very specific thing. What represents a state in quantum mechanics? You said wave
An element
function.
of Hilbert space.
Well, wave function would be very specific, but there's more general possibilities. Say a spinning
I mean,
electron is
because there
not.
are spinners also, like other type of. Yes, yes, sir.
Yeah, but in general, what would you
Elements of
say?
Hilbert space.
What kind of mathematical object? Yeah,
Are in
Hilbert
Hilbert
space.
space.
What about Hilbert? A given state is represented by what? Sorry, I couldn't get you. It was garbled a bit.
A vector
When
in
you said
Hilbert
in
space.
a vector in Hilbert space, does everybody agree? Or are there any disagreements? More importantly, is the given state represented by a vector in Hilbert space? Or let me be more precise. Is there a one-to-one correspondence between states of a physical system and vectors in a Hilbert space? In the quantum mechanical description of the system.
Sir, if there are some states that are not normalizable, so can they represent physical state? I don't
So
think
states
there's
which
a
are not
one-to-one
normalized,
relation.
you mean states which are not in your Hilbert space, right? Normalizability is just what helps you to decide which Hilbert space you are in. There are other Hilbert spaces, for example, finite dimensional spaces where normalizability is trivial. What you mean to say is there may be some states which cannot be described by elements in your Hilbert space. Frankly, such states don't really exist as physical states. They are more mathematical objects which we use to help in our description. But there's a much more fundamental thing here. For every vector in Hilbert space, of course, there is a state. Is the converse also true? For every vector, there is a unique state, right? A given vector cannot describe two states. What about the converse?
So you mean for a
Anybody?
given physical state, can there be two elements in the Hilbert space?
Hilbert space, yeah.
Scaled vectors represent the same physical state, right?
Great.
Like just parallel vectors are.
Yeah, that's the
represent
point.
same-
The point is that is exactly the point. The point is the correspondence is really not one-to-one. There are infinitely many vectors in your Hilbert space which stand for the same state, right? All vectors which are multiples of each other. The multiples may not really be just scaled because you could have multiplied them by a complex number with magnitude 1, for example. That is typically the most common thing that you do. You work with normalized vectors only, but even then you can multiply a normalized vector by a complex number with magnitude 1, a pure phase, so to speak, and that will still describe the same state. Right? That's a trivial statement. All of you know this. But what is perhaps not so obvious is that this actually makes this issue of operators in quantum mechanics a bit tricky, if you really think about it. Well, what are the operators supposed to do? Operators are linear operators which act on vectors in the Hilbert space, right? But what you're really interested in, physically, is the way in which states transform. And a given state actually stands for infinitely many different vectors. In other words, okay, there's a technical term for this. All these infinitely many vectors, which are multiples of each other, and hence stand for the same state. Do you know what they're called? The collection of these infinitely many vectors, multiples of each other. What is the name for this?
Multiples of each other means linearly dependent.
Not just linearly dependent in a very specific way. Three vectors can be linearly dependent if, say, psi3 is C1 psi1 plus C2 psi2. But here we are saying psi3 is C1 C3 times psi1, psi2 is C2 times psi1. All multiples of a single vector. Not just linearly dependent. The point is they form a vector space on their own right, a one-dimensional vector space, because there's only one independent vector. Every other vector is a multiple of that. But a one-dimensional subspace in a vector space has a very specific name. If you think about what it looks like, say, in ordinary 2 dimensions. In ordinary 2 dimensions, what would a one-dimensional subspace look like?
A straight line passing to origin.
Yeah, a straight line passing to the origin, right? So basically, you can picture quantum mechanical states essentially like as if they are not just vectors in the Hilbert space, but basically straight lines passing through the origin. Although, of course, there's a complex vector space, so that visualization is really not possible that way. But you can imagine that it has the same properties as a straight line passing through the origin of your Hilbert space. So each straight line actually stands for a state. Okay, and so physics really should not depend on which vector from this ray. Okay, that's the technical name for this. This set of all this one-dimensional vector space which you get by taking all multiples of a single vector is called a ray. Ray just like a ray of light. That's a ray essentially is what a straight line with infinite extent looks like. Okay. So technically speaking, states in a quantum mechanical system actually are in one-to-one correspondence with rays of the Hilbert space, not with vectors of a Hilbert space. Okay. So this should be pretty common knowledge to all of you, right? You already knew this, you may not have known the words. Is that okay? I hope you already knew this, right? So when you say a symmetry transformation, and in fact, when you say any transformation, what you are really saying is something happens to the physical system. That means a ray in the physical system that stood for a state, that changed into some other ray, right? Now, the reason why we don't work with rays but prefer to work with vectors is simply because vectors has this beautiful property of linearity. You can add vectors. You can multiply vectors by scalars. That beautiful structure, which actually makes linear algebra possible, is not available for rays. You can't add two rays, right? And anyway, tell me why you can't add two rays? Suppose I have a ray like, okay, but this is bad drawing, but suppose these are two rays, both going to the origin. So any vector here, any vector in this ray would be along this line. Any vector in this ray will be along this line. You can, of course, add these two vectors, but I'm claiming that you cannot use that to add two rays. Why not?
Sir, you can construct two rays if you add them, as in.
How?
As in, I mean, one of the angles is a smaller angle, the other is a larger angle. So,
True.
I don't know. I think there can be two rays if you add them.
You mean one going this way, one going this way?
Yes, maybe.
One like this, one like this.
No,
Yes.
you'll get many rays depending on what the different, like if you consider the vectors from these two rays, depending on the scalar in front of the vector, you'll get many different rays. So
Yeah.
adding two rays won't just give you one ray.
That's exactly the point. The point is, you could always choose vectors from your rays, but if you chose these two vectors, for example, then the sum would of course be something like this by using the parallelogram law, and that will give you a ray like this. But I could very well have chosen the vector from this ray not to be this one, but to be this one, let's say a longer one. Of course, my drawing is bad, but you have to realize that I intended to keep this ray along this line. But now if I did this, then the ray will be something like this. There is no well-defined way of defining addition of rays, which is unique. The point is, you can define addition of vectors, and vectors belong to rays. But the trouble is, this will now then depend on which particular vector you choose, right? Remember, we had seen several situations like this when we use group theory, for example. When we define, say, the isomorphism between quotient group and the image, there we had a possibility of, or even something like that when we label a particular coset. We label it using any one of the elements of the coset, right? GH is the same as G prime H as long as G and G prime belong to the same coset. But then when we go on and define, say, the result GH into G1H into G2H is G1, G2H, at least for normal subgroups, then this result does not depend on which particular label you have chosen. That is why you could make this a well-defined definition. Here, there is no such way. You cannot have a well-defined definition of addition of rays. So linear structure is out. So this is precisely why, despite the fact that rays are really what you want to work with, you can't. You have to work with vectors, and then keep track of the fact that actually states are always really represented by rays and not vectors, and which is precisely why when you're choosing one vector out of array, you insist on normalization. That normalization thing is really to make, at least cut down on the infinitely many choices a bit. But even then, because you're dealing with quantum mechanics and you have the possibility of multiplying by phase factors, even that does not uniquely specify your vector. You have to live with that kind of phase redefinition possibilities, which actually is going to be very important in the proof of this theorem. Okay, so coming back to what this theorem really says, first let's define what a symmetry transformation is. So it is a ray transformation. That's the first point. It's a transformation capital T which carries rays into other rays, because it carries states to physical states to other physical states, right? So there is one thing you have to bear in mind. What you're doing is doing to a system changes its states. So it changes our description of the states, but what it really changes are the rays, not the vectors directly. So basically what you are saying is, if you take a vector psi1 from a ray R1 and a vector psi2 from a ray R2, then R1 under this transformation goes to another ray TR1, R2 goes to another ray TR2. And basic idea about quantum mechanics is that the probability amplitudes will not change under a symmetry transformation. That is exactly what a symmetry transformation is defined as. So the basic definition of a symmetry transformation would be that no matter what psi1 prime you choose, we are all going to confine ourselves to okay, we don't even need that. Sorry, we don't need that. The point is, whatever rays you choose, you ultimately must end up with this result. Whatever vectors you choose from the rays, psi1 prime from TR1 and psi2 prime. We take psi2 prime from TR2. Then psi1 prime, psi2 prime inner product. When you take the mod square of that, that must be equal to psi1, psi2's mod squares inner product. Okay, so that is important. At least you have chosen normalized states to begin with. That is the definition of T, the question of a symmetry transformation, which really is a transformation between rays. What we are really going to try to do now is show that with this definition of a symmetry transformation, it is possible to define an operator which acts on the states and produces new states, such that when psi1 belongs to R1, psi1 prime, this operator U acting on psi1 belongs to TR1, and this particular result is obeyed. And in addition to this demand, we only demand one more thing. At least as far as the proof of Wigner's theorem is concerned, we demand that this transformation also has an inverse, which is symmetry preserving in the same sense. That is, or rather, not really symmetry preserving. Wrong terminology. What I really should say here is probability amplitude preserving. Or probability preserving. Because it's a mod square which has to stay the same. Now, I'm very sure most of you might be thinking that what's the big deal here, because if psi1 prime is U psi1 and psi2 prime is U psi2, where U is unitary, then this result would be automatic, right? I hope everybody is familiar with this notation. Psi1 comma psi2 for the inner product. Yes?
Yes, sir.
And of course, we might like this one better, at least physicists like this one better, but mathematicians hate it for the simple reason that this notation is basically, basically builds into it linearity. So the moment you have anything which is not linear or a possibility of a nonlinear transformation, then Dirac's notation fails spectacularly. That's not a shortcoming of the notation. It's basically the point is Dirac's notation has linearity inbuilt into it, so that many of the things that you do automatically when you use bras and kets, well, actually are rather deep things which you can do without even thinking, simply because, simply because the notation makes that possible for you. Let me just give you one example of that, because that's something which I'm not sure whether I've talked about this before. I may have, because in a quantum mechanics class I may have talked about this, but let's just point out that when you say something like this quantity, what does this really mean? Mathematically, what does this mean? What does this quantity mean?
It'll give you a scalar. It's taking the inner product between Chi1 and the vector you get by applying A on
So
Chi2.
basically what we're saying is this is what you are going to get, right? Chi1 and A Chi2, right?
Yeah.
And that's a scalar. It's a feed, it's an element of the feed. A complex number right now for us. Okay, fine. So this is what it really means, right? So when you write this in the inner product notation, it's obvious that A is acting on Chi2 producing a new vector, and you are taking an inner product of that with Chi1, right? But notice that this notation, the Dirac notation, is a lot more symmetric than that. It's A which is sandwiched between a bra Chi1 and a ket Chi2. So don't we often do this? We do it all the time. Is A acting on Chi2 or is A acting on Chi1?
It will be the A dagger acting on Chi1.
Really?
The conjugate.
Do you mean these two are equal, right?
Yes.
Okay. But this notation doesn't really mean that. Firstly, the important point is A dagger Chi1. This A dagger, which vector? Suppose you have a vector. You remember you had a vector space. Let's call that V, in which your kets live. There's another vector space V star in which your bras live, right? This A operator, does it act on kets or on bras?
On the kets.
But when you apply ket Chi1, when you do calculate this first, you often do this, right? Very often it's easier. For example, if you are trying to calculate something like, let's say MAN, where for harmonic oscillator basis, then either talk of AN or MA, right? You do it all the time. In fact, that is exactly the beauty of Dirac's notation. You can do it all the time. But you have to think about it a bit. The same operator, can it act on two different vector spaces?
Sir, in the case of the Dirac operators, we were talking about wave functions belonging to the same.
Not really. First of all, Dirac operators go way beyond wave functions. And moreover, frankly, in the moment you write this as bras and kets, you're talking about two different kinds of objects. Kets are vectors in your Hilbert space, bras are linear maps which act on vectors to produce numbers. And if you have done any linear algebra, you would know that every vector space has a dual space made out of linear functions like this.
There's a one-on-one map between those two spaces.
True, but the question is, which one does A act on? Does it act on the kets or the bras? An operator, after all, is a function, right? It's a function whose domain is a vector space and its range is also a vector space, right? Now, for a function to be well defined, its domain has to be very precisely defined. You can't have the same operator actually act on both bras and kets. Two different vector spaces. How can the same operator act on both?
Sir, is it something like, so if let's say A is acting on bra, but then A can also act on ket because of the one-on-one map between bras and kets? So technically through that map we can induce.
Not really, not really. It's actually more like, is related to that, but it's deeper than that. The point is, you can, the operator A, which when you think of, strictly speaking, what you're doing is this. You can think of this as psi1, A psi2. That was the original meaning that was stated. The operator A acting on case. You can also think of this as this. But now this operator A is not at all the same operator as this operator A. Point is, corresponding to every operator in your original vector space, there is a unique operator which acts on the dual space, such that for this unique operator, psi1, this operator gives you a new bra, that acting on psi2 gives you the same result as this one. So basically, these are two different operators that we are talking about, not the same operator. You can't have the same operator. Same operator can't act on two different kinds of objects. Okay. Now the beauty of Dirac's method notation is, you can simply forget about this distinction and happily use A either on the left or on the right. The notation is designed to make that automatic. But the notation is designed to make that automatic only if the operators involved are linear operators. For anything which are non-linear, especially, well, non-linear, you might say, why bother about non-linear operators? There are no non-linear operators in quantum mechanics. The answer is there are. At least there's one kind of operator which is not linear, the anti-unitary operators. Okay. So in general, by the way, the A-dagger operator actually acts not on the bras, but on the kets themselves, on the original vector space. Note that here, when you write inner products, psi1, psi2 is an inner product between two vectors. It's not a bra acting on a ket. It might be equal to the action of a bra psi1 acting on a ket psi2. Not might be, it is. But that is because through the inner product, you can define for every ket a corresponding bra, which is the one-to-one correspondence we were talking about. But here, really, both of these are kets. So when you talk of the A-dagger, A moving from here to here and becoming A-dagger, which is perfectly right. But that actually is a situation for action on kets or action on vectors, not on dual vectors. A and A-dagger both act really as they're defined on the space. So whenever you're using the thing on a bra, you're really using a different operator altogether, which is somehow, which actually, you can show that there exists an operator which acts on the dual space, for which this two-facedness sort of is automatic. And that's exactly what is built into Dirac's notation, which makes Dirac's notation such a nice thing to use. Because you don't have to keep on worrying about what you're acting on. You happily apply the same operator or what looks to you like the same operator on the ket or a bra, and it works. Okay, it doesn't really, but Dirac notation sort of hides all those things from you. And because it hides all those things from you, it's very easy for us to use. And it's also, for the same reason, it's very, very confusing for the mathematicians to use. Most mathematicians hate this notation. They would definitely use this. Now, we are not mathematicians, but why we are using the inner product notation is simply because of the fact that Dirac notation is wonderful for linear operators, not so wonderful for anti-linear operators, which an anti-unitary operator is. So because a general symmetry transformation, according to the theorem that we are trying to prove, actually contains both linear and non-linear operators, or linear and anti-linear operators to be precise, we are actually sticking to this inner product notation. So I hope everybody is familiar with this notation, so there will be no confusion. You can, for the time being, think of this as a ket acting on a bra, but please don't, because that might get confusing later on. This is just the inner product of two vectors, and the important point is your symmetry transformation has to be such that this works. Okay, so that is the premise of Wigner's theorem. Now, as I have written up here, there's one wonderful book which, okay, it's a bit too much to call this wonderful because it's a horribly complicated book as well. if you go into the later parts. But this part, one of the best expositions of the proof of Wigner's theorem, a much better proof than that you would find in, say, Wigner's book, for example, is in Weinberg's quantum field theory, first volume. So anybody who wants help with the homework can definitely look at this. But please don't copy from Weinberg. Weinberg has a rather unique style. If you copy from it, it will be obvious for me that you have copied. You definitely should take a look, perhaps to fill in the blanks that I'm going to leave here in the proof. I'm going to quickly skip over to the basics of the proof here. So let me just point out that you should realize what we are trying to prove. We are trying to prove that for any symmetry transformation, which transforms rays, R1, R2, R3 goes over to TR1, TR2, TR3, and so on, we will be able to find, we will be able to choose vectors from the rays in such a way that an operator acting on that vector will give you an operator in the resulting ray, and that operator will be linear or antilinear. So that is what we are trying to prove. That's not automatic. You may, if you choose your operator, your vectors differently. For example, it's obvious that I could choose, when the transformation is between this ray and this ray, I could choose an operator which transforms this one into this one, which is not length preserving at all. Or I could choose an operator which transforms this one into this one. Same length, different direction, which is sort of what a unitary operator does. But that's a choice. You don't have to do it. The fact that you can always do it, you can always make this choice, is essentially what Wigner's theorem tells you. Okay. So what we also demand is, of course, that the transformation has an inverse, which is probability preserving in the same sense. Now, in order to go ahead with the proof, what we will do is we will start with a set psi k, a complete set psi k on your vector space, such that psi k's are all orthonormal. So psi k comma psi l are delta kl. Okay. So psi k belongs to, of course, each of these psi k's, they belong to different rays. They are definitely not multiples of each other, because if they had been multiples of each other, they couldn't have been orthonormal to each other, right? So all of these, so I start by choosing a basis, an orthonormal basis on my vector space, psi1, psi2, psi3, whatever. For each psi1, psi2, psi3, there is a ray R1, R2, R3 corresponding to psi1, psi2, psi3, and so on. And then whatever transformation we are thinking about, this symmetry transformation, let's apply this on our rays. R1 gives me TR1, R2 gives me TR2, and so on. And then what we are going to do is we are going to just choose some rays psi k prime from TRK. Okay. All these rays are normalized. They have norm of unity. All these vectors are normalized. They have norms of unity. But there are still a lot of possibilities of choice, because you can multiply them by any phase factor. Now, because psi k prime belongs to TRK, so if you take the psi k prime, psi l prime inner product, take the mod square, according to our definition of symmetry transformation, this has to be the same as psi k psi l mod square. Now, psi k psi l mod square is, of course, the square of delta kl. And you all know that delta kl, when you square it, it gives you back delta kl. So psi k psi l, psi k prime psi l prime mod square is delta kl. My claim is, this immediately tells you that psi k prime psi l prime inner product, not the mod square, but the inner product, is also delta kl. How do I prove that? All that symmetry transformation has proved for us is inner products of psi k prime psi l prime. Psi k prime is what I get when I pick any vector from TRK, psi l prime picked from TRL. So their inner products modular square is delta kl. I've proven that. How do you go from there to the statement that the object is still delta kl? Yes? After all, if you know something as a magnitude of 1 or 0, they could be phases. So why am I claiming that psi k prime psi l prime has to be delta kl? couldn't I have done something like this? Where phi could depend on K
But
and
how
L.
will
Yeah, go ahead.
I mean, if K and L are different, so it wouldn't matter anyway, right?
Of course, if K and L are different, it wouldn't matter. That's a wonderful point. Then, but if K and L are equal, then it wouldn't matter, right? You're very close to the answer. You almost got there.
I mean,
If K and L
if you
are
normalize
different,
K and L are equal, then it.
So point is somehow this can't be there. As you are saying, if K and L are different, it doesn't matter whether it's there or not because it's zero anyway. But if K and L are equal, a non-trivial phase would actually change the thing, right?
But you have to impose some condition on Q, right? I mean, okay, no, it's a phase anyway. Okay.
No, it's not a condition. I didn't impose any condition.
Okay.
In fact, the answer is written on the screen, so you should be able to read what is written right next to it.
Then R plus.
The point is, if
It's
K is
real.
equal to L, you are actually taking psi K prime with psi K prime, right?
Yes.
And psi K prime with psi K prime has to be a positive real number.
So,
The
but
inner
then-
product of any vector with itself has to be positive and real. Or it can be zero if the vector is a null vector, but otherwise it has to be a real positive number, right? So because we already know it has a magnitude of 1, it has to be 1. Is it okay?
Okay. Yes, sir.
Of course, what I wrote here is a shorthand for what I really meant to write, psi k. Inner product is a positive real number. That's why there's no e to the I phi kl. Okay? So psi k, just like your original psi k psi l, this psi k prime psi l prime, this set has to be orthonormal. Now you might say, how can that be? Because after all, I have a free, for any vector, in any ray, I have a free choice, right? Whichever vector I pick. So how can all these, so for even if I fix my psi k is fixed, but the psi k prime, suppose I fix that, I still have infinitely many choices about psi l prime, right? How is it still possible that I'm going to get delta kl for all of them?
Sir, we could probably express those other infinite possibilities as a linear combination of orthogonal basis vectors.
Look, I'm actually talking about very specific vectors. I'm saying that psi k, psi l we started with, then you have different rays to which psi k's belong, right? Rk. So after the transformation, Rk transforms into Trk, another ray. And I'm saying that I will pick some psi k prime from Trk. I'm not saying which, right? I'm saying I will pick some psi l prime from TRL. And then I'm going on to show that because of our demand of symmetry, that the probability amplitude stay the same, it follows that psi k prime and psi l prime has to be equal to delta kl. Doesn't that contradict the fact that you have infinitely many possible choices? Suppose I change my psi l prime instead of choosing this one, for which maybe psi k prime, psi l prime was delta kl. Maybe I change it after that. I take some other psi l double prime, or psi l double prime from TRL. That's my free choice, right? Once again, I think you are thinking. Sorry, I couldn't hear you. I couldn't really, because I couldn't draw them for the simple reason these are complex vectors, right? In fact, the whole point is they're all normalized. They all have length 1, but they differ by phase factors. So, okay, let's give it a try. Psi k, actually, if I take this, I have a full circle of possibilities that I can take this vector and put any phase on that. Psi l, I could take this vector, put any phase on that. So my question is, okay, for one particular choice, maybe I get psi k prime, psi l prime is delta kl. If I change the choice, You'll still get delta KL. Actually, that should be pretty easy. Even in think in terms of ordinary 2D vectors. Say for these two vectors, they're perpendicular, right? Let's say that's the delta KL. Maybe they are unit length and delta KL. Now let's forget the delta KL for the time being. But if I change the L, change this vector into something else, won't the fact that psi k prime, psi L prime is 0 when you have chosen different rays, won't that still be true? All I'm saying is that if you change your psi L prime, you're actually picking up an extra phase factor on psi L prime, right? The inner product, of course, will change. Inner product will get multiplied by that phase factor. But since the inner product is 0 here, multiplying by a phase factor, how does it matter?
Yes, sir.
Okay. And the non-zero cases when K and L are the same, it's pretty easy to see that if you change by a phase factor, the fact that there is linear in one component and antilinear in the other automatically cancels the phase factor. Okay. Now my claim is psi k prime is also a complete set. That is, just like the original set was complete, this set is also complete. How do you prove that? The proof is rather simple. The proof essentially says that if it were not complete, that means there would be some state psi prime which is orthogonal to all the psi k primes, right? If the psi k primes form a complete set, that is any vector can, remember all the psi k primes are orthonormal. So if I can find, if any vector could be expanded in terms of the psi k primes, then there will be some component in the direction of that vector. Then that component can be found out by taking the inner product, right? Psi prime comma psi k prime will give you that coefficient. And so if psi k prime were 0 for all psi k prime, the only possibility would be psi prime is 0. So can psi prime be not 0 and still have an inner product of 0 with all the k's? That of course is possible only if your space is not spanned by the psi k prime. Okay, again, simple picture in 2 dimensions. Again, ordinary 3D vectors, x and y. Okay, they are orthogonal. Okay, ex, ey, let's say. They are orthogonal, but they don't span the entire space. As a result, you can find a vector which is orthogonal to both of them, namely Ez. But that's because Ex and Ey were not a complete set on your space. But suppose your space were 2-dimensional, Ex and Ey were really complete, then you would not be able to find a non-zero vector which is perpendicular to both Ex and Ey. Okay. In 2D, there is no vector which is perpendicular to both of them. In 3D, there is no non-zero vector which is perpendicular to Ex, Ey, and Ez. That's all we are saying here. That if we are assuming that psi k prime is not complete, so this is a proof by contradiction. All we are saying is that if that were the case, then we would be able to find a non-zero psi prime which is orthogonal to all the psi k primes. Is that okay with everybody?
So we can just have one that needs to be linearly independent, right? Not
Right.
necessarily
Not
orthogonal.
orthogonal, right? But you also know the Gram-Schmidt orthogonalization procedure. You manage to find a non-linearly independent one. That of course proves that it's not complete. But for our proof, it's easier to handle if it were orthogonal. Okay. But they're equivalent statements. If you manage to find one vector which is not which is not linearly independent, not linearly dependent. If you manage to find one vector which is linearly independent, you can always find a vector which is orthogonal. That's the Gram-Schmidt orthogonalization, standard procedure. Okay. So linear independence and the existence of an orthogonal vector are one and the same thing. And the advantage of using this is, here is where this inverse transformation also exists. This comes in. The point is, just like T exists, there has to be a T inverse as well. So if psi prime, our vector, belongs to a ray R, then let us consider T inverse R. T inverse R is basically the ray which would have mapped onto R after the transformation. So, and let's take a psi double prime, a non-zero vector which is in T inverse R. Okay. So now notice psi k and psi double prime, these are vectors from rays before the transformation. If you take their mod square, their inner product, and take the mod square of that, that has to be equal according to our definition. Psi k maps into psi k prime, and psi double prime maps onto, actually it's not psi double prime which maps onto, but psi double prime belongs to T inverse R this way, which maps onto the ray R in which psi double prime belongs. And for any ray in that, you have to have this possibility that this must be equal to this. And since this is taken to be 0, remember, that's what this one has to be 0. Sorry, this is not psi double prime. Typo, or what do you call it? Call it when you make a mistake, when you write something down, you can't call it a typo, right? Is there a word called write to or something? This thing, so psi prime, psi double prime, of course, is in the original ray. Psi prime is our orthogonal vector, which is orthogonal to all the psi k primes. What this says is psi double prime, the vector which belongs to T inverse curly R, must be orthogonal to all the psi k's. And it was a non-zero. And now that's a contradiction, because you cannot have a vector which is orthogonal to all the vectors in a complete set. Psi k's are already assumed to be a complete set. That's what we started with. And yet be non-zero. So this contradiction shows that the set psi k prime is also a complete set, which essentially says that you should be able to write down any vector in your Hilbert space as a linear combination of the psi k primes. This is what we are going to use. Okay. Now, this is important. After all, we need to choose the psi. After all, we are making a choice of the psi k primes, right? So let's make a choice by establishing a phase convention. What we do to establish the phase convention is something like this. We first choose any one of the psi k's as a special psi k. That's just a choice. Let's say we choose psi 1, okay, as special. And consider this particular linear combination, gamma k, which is 1 by root 2 times psi 1 plus psi k. It's easy to see that mod of gamma k is how much? Gamma k is a vector, a linear combination of psi 1 and psi k. What is the mod of gamma k? Norm, or how much is that?
1.
1, right? Why is it 1?
Because psi L and psi K.
Psi 1. This is not L. This is 1.
Oh,
A specific. But it would work for psi L as well. But this is a specific psi. I'm using this to make a particular choice.
yeah. So it's because of the orthogonality and like.
Because psi 1 and psi k, just like all psi L, psi k, psi 1 and psi k are orthogonal. And so, and then it's the standard property of the inner product, right? Of course, this seems obvious because when you have two vectors with unit norm and you add them together, and they're orthogonal, which is very important, then the standard normalization for the sum is 1 by root 2 times this plus this, right? That's what you have learned all along. But you have to realize that there is a whole host of properties of the inner product, orthonormality of the basis, which is inbuilt in this C1 mod square plus C2 mod square, etc. equal to 1. This thing that you do use all the time in quantum mechanics. Okay, fine. Now this is your gamma k. I've just started with this vector. 1 by root 2 psi 1 plus psi k. I'm starting with that. So it's not one vector. It's actually all k's. That is infinitely many of them. The only thing that I'm not going to use is k equal to 1. Okay, apart from that, psi 1 plus psi 2 by root 2, psi 1 plus psi 3 by root 2, and so on. I have gamma 2, gamma 3, and so on. Now, this gamma k will belong to some ray in your vector space, and under T, your transformation, this Sk, this ray, will go to some other ray Tsk. So let us pick any vector gamma k prime from Tsk. Okay. Now, one thing I do know, gamma k prime is a vector in your Hilbert space, and because it's a vector in your Hilbert space, it can be expanded in terms of the vectors which are already there as a basis. So what is the basis that you have? You had the original Psi k's, that they were a basis. But the Psi k primes are also a basis. That's what we just established, right? They're orthonormal and complete. So I can write gamma k prime as a combination of Psi L primes with, of course, coefficients which will depend both on the k and the L. It will definitely depend on L, and since the vector you're talking about depends on k, the coefficients will depend on k. Now, using the fact that this thing belongs, remember, this thing belongs to what? This thing belongs to T. This Psi L prime, this belongs to T RL. This belongs to RL. This belongs to a new ray called SL. Okay. And gamma k prime belongs to T SL. And the basic property of any symmetry transformation is, if you pick vectors from TSL, TRL, then the inner product mod square must be the same as the inner product mod square here. And that immediately tells you that CKK, this coefficient, if you use this, is of immediate the CKK mod square, and CKL mod square must be 1 by 2. And for all other CKK and CK1 gives you 1 by root 2. And CKL for all other L must be 0. That is an immediate consequence of this. Of course, it only talks about mod square. CKK mod square has to be 1 by root 2, 1 by 2. So CKK mod has to be 1 by root 2. Okay, and CK1 mod has to be 1 by root 2. Okay. Right? Is that clear?
Sir, I just one small question. When we say a set of vectors span the vector space and the set of vectors form a complete set, are these two statements equivalent?
No.
Or not?
They might span and not be linearly independent. Right? They may be overcomplete.
Yes, yes. I mean, in that case, there will be more. There will be more. There will be more than the number of basis vectors.
Well, more or less, that's actually something you can use only for finite dimensional vector spaces. These are typically most often infinite dimensional vector spaces. So more or less is not something you would like to use. Even the result that bases can be put into one-to-one correspondence with each other actually works only in infinite dimensional vectors, in finite dimensional vector spaces. And you know that, right? Have you? Okay, can you think of two bases which are used in quantum mechanics for the same space which cannot be put in one-to-one correspondence with each other?
One is,
Where you have all used this.
When you
use? Yeah, you have all used this, by the way. Everybody here in this class has used bases in quantum mechanics for the same space which cannot be put into one-to-one correspondence. Yet they are linearly independent and spanning.
I think J square, J1 square, J2 square, that one you mean. And the other one is, I think, J1, J2, and J1Z, J2Z.
Well, sorry. That's actually the opposite example. The number of states so there are exactly equal. They are in one-to-one correspondence. And in fact, you can show that they're in one-to-one. You have shown that they're in one-to-one correspondence, by the way, in the previous class. That's the whole point in the Clebsch-Gordon sum. You would find the total numbers of the dimensions stays the same.
You mean the number of basis vectors are same, right? I mean, in both those bases.
Yeah, both those cases. They're infinitely many, but you can have one-to-one correspondence between each one of them. Because within each subspace, they are actually finite and they're equal numbers. But you have used, everybody has used, it's one of the most common basis choices that you make. Okay, when you worked with the one-dimensional harmonic oscillator, when you were using wave functions, what was your actual choice of basis?
Position basis.
Hmm?
The position basis.
The position eigenkets, right? Okay, so they are infinite in number, but they are uncountably infinite in number, right? Because the number of points on a line, that's uncountably infinite. But on the same space, you have actually used a countably infinite basis. Does anybody know which one? Or everybody knows which one, but does anybody recall what I'm talking about?
Eigenstates of Hamiltonian. They are
Which
countably
Hamiltonian? Which Hamiltonian?
infinite, I guess.
Which Hamiltonian? You're close, but which Hamiltonian?
Of the simple harmonic oscillator.
Yeah, exactly. The number, you have used a number basis, right? You use both the number basis. In fact, you have used them equally, right? Whenever you did things in the position space, you have used the position basis. Whenever you worked in using the so-called operator method in harmonic oscillators, you have used the operator that basis, right? Yeah. So these two bases are, of course, bases for the same space, but they are definitely not in one-to-one correspondence with each other. So forget being equal in number. That only works for finite dimensional vector spaces always. For infinite dimensional vector spaces, that's not guaranteed at all. Okay. So one is countably infinite, the other is uncountably infinite. You definitely can't put them into one-to-one correspondence with each other. Okay, now coming back to this, I am sure everybody can figure out why this happens. This is just calculate gamma k gamma psi l, which is 1 by root 2 for that is for this ck1 is 1 by root 2 and the ck. So gamma k psi 1 and gamma k psi k are 1 by root 2 each, and these are ckk and ck1 for those cases. For all other L, gamma k psi L is going to be 0, and you just use that, you get these results. Now this is fine. This is what our original definition tells us. But for any given k, we can choose the phases of the two states, gamma k prime and psi k prime. So that's what is fixing the phase for us. We are going to choose the phases in such a way that gamma k prime and psi k prime will be chosen so that ckk and ckl are given by 1 by root 2 each. So they are chosen to be real positive. Okay. Note that once you have made this choice, your freedom is gone. You no longer have the freedom to change your phase, because then these coefficients would also change. Could pick up phase factors. Okay. Right? But now we have got very close to our final goal. We want to have an operator which acts on our original states in the original rays to produce states in the new rays, and show that that operator is either linear unitary or antilinear anti-unitary. So let me quickly go through the proof. What we are going to do is we are going to define the operator U by at least saying this much about it. This gamma k prime for which the phase has been chosen, so that ckk and ckl is 1 by root 2, you're going to call that U gamma k. Okay. And psi k prime, again, for which the phase has been chosen here, is what you are going to call U psi k. So you're defining an operator now. You have just told me that when U acts on psi k, it produces psi k prime with this particular choice of the coefficients there. And when U acts on gamma k, it actually produces, which is 1 by root 2 psi 1 plus psi k, remember? So 1 by root 2 psi 1 plus psi k, U acting on that gives you U gamma k, gives you this result. Okay. Question: why is this not a trivial thing to say? This looks trivial, right? U acting on this gives you this. Why is this not trivial?
Linear?
Yeah, it looks trivial to all of us because we are used to dealing with linear operators all the time. Here we have no clue whether this operator U, at least at this stage, we have no clue whether this operator is linear or not. All I have told you is this: what does this operator do? X on psi1 to give you psi1, psi2, psi3 to give you gamma 1, gamma 2, gamma 3, and X, because remember this is for all k, and X on gamma 2 prime, gamma 3 prime, gamma 3 prime to give you gamma 2, gamma 3, gamma 4, etc. to give you gamma 2 prime, gamma 3 prime, gamma 4 prime. So you have not told me what U does to all vectors. You have just told me what U does to a specific bunch of vectors. Now, from linear algebra, you must remember that if I specify the action of an operator on a complete basis, does that specify the action of the operator on every vector? Do I specify what the operator does on a basis vector, on the set of basis vectors? Does it tell me what the operator does on every vector?
Could you repeat?
If I tell you what an operator does, yeah, the question is, if I tell you what an operator does on every vector, or sorry, every basis vector, does that tell you what the operator does on every vector? Yes or no? Again, another obvious question. Could have another obvious answer. Haven't you seen that done all the time? You have defined the action of an operator by what it does to the basis. We have done this in this class a lot, right? We have picked up a basis set E1, E2, E3, and then applied the operator on that and told you what happens to that. So is it correct to say that the operator, if you know the operator's action on the basis vectors, then you know the operator's action on all vectors?
Do we have to assume linearity there also?
Exactly. If that were really the case, then this proof would have been trivial. I wouldn't have to say anything more. Because if I've told you what U does to all psi1, psi2, psi3, I've already told you what U does to every vector. There's no further choice. But what you have rightly pointed out is this. That assumes that you're dealing with linear operators. Now, much of what you have done in linear algebra presupposes linear operators quite naturally. And as a result, sometimes those things sort of get so ingrained in the way you think that when you're faced with other options, like this one, right now we don't know whether this operator is linear or antilinear or whatever. We have no clue. So we cannot just claim at this stage that we know everything that it's going to do to every vector. We just know what it does to the basis vectors. In addition to that, we know what it does to U gamma case. That is U gamma 2, U gamma 3, U gamma 4. We know how much that is. Okay. Now, in order to be able to say what U does to all vectors, I have to start with an arbitrary get psi, some arbitrary sum of ck psi k, and from that, ask what U does to that. Okay. So now, okay, we are not close to the end of the proof, but we are close to what I'm going to talk to you about. The rest you have to fill in yourself. So if you consider an arbitrary state psi, which is sum over k ck psi k, which belongs to some ray r, then of course this ray will transform to some other ray tr, and you can take any vector psi prime from tr, and you can write it like this. Does everybody agree? Yes or no? Just to remind you, U psi k are exactly what we have been calling psi k prime so far, except that the phases of psi k prime has now been fixed. So while before we were saying psi k prime is any vector in trk, now we are not saying that. We are saying psi k prime is a specific vector in trk which gives you those ckk ck1 equals 1 by root 2. So is this correct to say now? Of course, if this were a linear operator, there would be nothing to say, right? This would be trivial. Except, actually, if this were a linear operator, I would have a ck here, not ck prime. This ck prime would all be equal to ck. And if it were an antilinear operator, the ck primes would have been ck star, ck conjugate. But given the fact that we don't know whether the operator is linear or antilinear, is this a correct statement to make? Yes? Can we at all make this statement? A rather trivial thing that I'm saying, actually. If you remember, what was the basic property of all the psi k primes? Psi 1, psi 2, etc. This formed an orthonormal basis, right? Psi 1 prime, psi 2 prime, what did they do? That's something we proved a while ago. We already it's rather trivial that psi 1 prime, psi 2 prime. Yeah. Go ahead.
Yes, could you repeat? I'm just losing connection with you.
Okay, I was just saying.
Could you just repeat the question?
The question is, this is your state. You started with an arbitrary state psi, some arbitrary state, so which can of course be expanded in terms of your psi case, with some coefficient ck. This belongs to some ray curly r. Arbitrary state, so some belongs to some arbitrary ray. Now this ray of course gets transformed to some ray tr, and we have picked psi prime out of that. And my claim is this psi prime can always be written down in this form, ck prime u psi k. That is, if psi is sum of k ck psi k, I can always write psi prime is equal to sum of k ck prime u psi k. Now, if u were linear or antilinear, we would know that that's possible, because if u were linear, then ck prime would be all the same as ck. And if u were antilinear, ck prime would be ck conjugate. My question is, given the fact that we neither know, do not know whether u is linear or antilinear, we don't know anything else about the operator u at this stage. We want to prove that the operator u we define this way is going to turn out to be either linear or antilinear, but we don't know that yet. So is it correct to say that I can write psi prime in this form? That's the question.
We had shown that psi prime k forms a complete set, right? So
yeah, exactly. We have already shown the psi prime k forms a complete set. So it doesn't really, I'm not really using any linearity or antilinearity property of u here. All we are saying that u psi k are essentially psi k primes with the space choice fixed, and they are a complete set. And now that because they are complete set, you can always expand psi prime in them in the story. So this is really rather trivial. You're not saying anything special about ck or ck prime. But now comes this very important point. Two important points, and this is where I will just almost close here. Well, psi k and psi, if you take the overlap and take the mod square, you must get the same result as psi k prime and psi prime's inner product mod square. That's a basic deal. The psi k is in one ray. Psi k, remember, is in curly rk. Psi is in some ray r. Psi prime is some vector in the ray curly tr, and psi k prime by definition is in trk. And this will definitely work for that. And that immediately tells you nothing else that if that is going to be correct, now what is psi k comma psi? If you take this psi, what is psi k comma psi? For this? Come on. This is trivial. If this is your psi, what is psi k comma psi? That's ck, right, as you should say. And what is psi k prime, comma psi prime? Psi k prime, remember, is our u psi k. What is that? By the same token, this has obviously ck prime, right? C prime k. Just this coefficient. So this symmetry demand tells you ck and ck prime must have the same magnitude. And then we already know that this one, of course, belongs to curly R. This one belongs to TR. But we have this gamma k, which belongs to this sk, some other ray. And this belongs to tsk, u gamma k. So that immediately gives you this result. Ck plus Cl mod square has to be Ck prime plus Cl prime mod square. So basically you have this equation between a bunch of complex numbers. The coefficient Ck must have the same length as the coefficient Ck prime. And Ck plus Cl has to have exactly the same length as Ck prime plus Cl prime. So that's the condition. Now what does this tell you? This is now, after this is just simple geometry of complex numbers. Since Cl mod square is the same as Cl prime mod square, if you divide the two, you can easily get this result, right? 1 plus Ck by Cl mod square, sorry, is 1 plus Ck prime by Cl prime mod square. This follows simply by this and dividing this by both sides by the fact that Cl mod square this remember is true for all k, including L. So that's what we have done here. Oh, sorry, I made a mistake here. This is not Cl, this is C1. And I'm dividing not by Cl, I'm actually dividing by C1. And C1 prime here. Okay. And this is also exactly the same. These are all C1s. Now, this Ck, okay, now the rest is simple geometry. Ck by C1, let's call this number Z, and the other side, let's call that Z prime. So let's call this Z, let's call this Z prime. So what does this tell you? It tells you Z and Z prime have the same magnitude. So if Z is here, what do you know about Z prime? So this is your complex plane. Yeah. So if
you can
know
make a
that
circle passing through Z.
And
it will
centered
land the
where?
same circle.
Centered where? I can make infinitely many circles pass through Z.
Origin.
Yeah, it's a circle passing to the origin. That has to be specified, right? You can't just say make a circle passing to Z. Any point can lie on the same circle as a circle passing to Z, right? I know what you meant the origin, but you have to be very specific about that because we are next going to talk about this one. So my Z prime has to be somewhere on this circle. Circle centered at the origin and radius, which is the distance, which is the length of Z. Z prime has to be somewhere here. Now, what does this tell you? It tells you 1 plus Z's magnitude is also equal to 1 plus Z prime's magnitude. So what does this tell you geometrically about Z and Z prime? Just like magnitude of Z equal to magnitude of Z prime told you that Z prime has to be on this circle, what does this tell you?
Circle centered on -1.
Yeah, so if you take a circle centered at -1 and passing to Z, Z prime must be on that circle as well. But that leaves you only two possibilities. Z prime has to be
Intersection point.
so how many times do two circles intersect?
2 times.
2 times, right? So either Z prime is here or Z prime is here. Either Z prime is equal to Z or Z prime equal to Z's conjugate. Of course, the other point, simple geometry has to be reflection on the real line, right? Which means in terms of the Argand diagram is the complex conjugate. So either Ck by C1. So there's a mistake which I have made simply because this must be my eyesight is going really. I sort of copied this from Weinberg and read this as CL, whereas these were all C1 because that's all you really need.
But sir, even if you keep it CL, I mean, it won't be a problem,
No,
right? As in,
it
you
will
could have
not
just
be a
defined it
problem in the
in the
long
first
run,
place.
but we can't say anything about CL right now, right? Because gamma k is defined to be Ck plus C1. That's because I've chosen C1 specifically. If I've chosen something else, then this would have been that. So you have two choices. Either Ck prime by Cl prime is equal to Ck by Cl, or Ck prime by Cl prime is the conjugate of Ck by Cl. These are the two choices you have. Okay. And then it's sort of trivial to show that from this and this, what you manage to show is U acting on Ck psi k. If you choose C1 prime to be equal to C1, that's your phase choice. You can always make a phase choice there. But the moment you choose C1 prime equal to C1, then and with going with this one, Ck prime will all be equal to Ck. Remember, this is not CL, these are all C1. So the moment you choose C1 prime equal to C1, this immediately tells you Ck prime has to be equal to Ck. And the moment you choose C1 prime equal to C1 here, if you choose C1 prime equal to C1 conjugate here, this tells you Ck prime is Ck's conjugate throughout. And that actually shows you that U acting on a superposition is actually sigma k Ck U psi k. Either that is for this choice, or if this were the possibility, then you have this. So which essentially almost ends up proving that U is a linear operator in the first case, antilinear in the second case. But there are some gaps here. Can you spot some gaps in this argument? In that one gap is what Wigner actually had left in his proof. And not only Wigner, almost everybody else, not all, in fact, everybody else after Wigner actually referred to Wigner's proof and had apparently not spotted that particular glaring, not mistake, but a gap in the proof which Wigner had made. Weinberg does a wonderful job of correcting that. Can anybody see what that gap is?
Sir,
Yeah.
I mean,
Yes?
I don't know, but is A by B whole star equals to A star by B star? Is it so?
Yeah, that's exactly what we're using here. But that's not the point. The point is, Wigner had proven, this argument proves that Ck prime by C1 prime is Ck by C1, either that, or Ck prime by C1 prime is Ck by C1's conjugate. And then because you can choose your phase once at least, then you choose C1 equal to C1 prime, then Ck prime comes out to be equal to Ck. With that phase choice, the operator becomes unitary, linear unitary. And in this case, what you do is choose C1 prime to be C1 conjugate, and then Ck prime comes out to be Ck conjugate. Done. And therefore, these are the two possibilities, and for these two possibilities, you get unitary operator acting, or U acting on Ck psi k is acts in a linear fashion. That's the first possibility. For the second possibility, it acts like an antilinear operator. Two possibilities: linear, antilinear. End of story. But there is a gap in the argument, and a very rather simple gap. It was such an obvious gap that most likely, I'm pretty sure Wigner thought about it. It seemed so obvious to him that he didn't even bother mentioning. But it is a gap. The gap simply is this. What does this prove? It tells you C2 prime by C1 prime is C2 by C1. What about C3 prime by C1 prime? What is that? If C2 prime by C1 prime is C2 by C1, what about C3 prime by C1 prime from this formula? We have already proven this, right? This is for all K.
C3 by C1.
For all C3 by C1, right? Okay, that's what everybody assumed. That's what Wigner assumed as well. But who is to prevent this from happening? That C2 prime by C1 prime is C2 by C1. But for another coefficient, C3 prime by C1 prime, you have C3 star by C1 star. After all, that's equally consistent with whatever we have proven so far. Remember, whenever we have proven, we have taken a particular gamma K for a particular K. Works for all K, right? But it does not work. There's no connection between K equal to 2 and K equal to 3. For K equal to 2, you end up proving this. K equals 3 also, you end up proving this. So now, the moment you are saying something like this, that when you choose C1 prime equal to C1, all the CK primes are equal to CK, that assumes that for all the Ks, you have either made this choice or made this choice. Right? But your proof doesn't really say so, as of now. The proof says for all K, either this or that. But what happens if I had this possibility, that C2 prime by C1 prime is C2 by C1, at the same time C3 prime by C1 prime is C3 star by C1 star. Whatever we have proven so far does not preclude that. And if that is the case, then your operator is neither linear nor antilinear. So the great thing about Weinberg's proof, which you will find in his book, Quantum Field Theory Volume 1, is that Weinberg plugs that gap. He actually shows that if you make C2 prime by C1 prime equal to C2 by C1, then C3 prime by C1 prime, C4 prime by C1 prime, etc., all will have to be C3 by C4, C4 by C1, and so on. You can't get you will not be able to mix up conjugates and non-conjugates. But that is a proof which Weinberg gives. Wigner somehow omitted. Okay. And in addition to that, there is one more gap in this proof, which actually Wigner had himself plugged. This is not the end of Wigner's proof. The point is, this particular statement has been made about a particular combination sigma ck psi k. Now, why is it? It could be possible. You might even imagine that this is possible. For some ck psi k, U does this. But for some other, let's say dk psi k, some other combination, U suddenly does this. So if U does this on ck psi k and does this on sigma dk psi k, of course, what this to be different, the coefficients have to be complex. If the coefficients are all real, you would not be able to tell the difference between this and this. But if the same U did this and this for different sets, then would it be linear or antilinear? Or what would it be? Any idea what other gap could there be? What kind of vector would this be? What kind of operator would this be? Linear or antilinear? A very simple question has a very simple answer. If you really did this, then the simple answer would be it would be neither linear nor antilinear. For a linear operator, this has to work for all vectors, all input vectors. For an antilinear operator, this has to work for all input vectors. Okay. So if You did this on some combination and did this on some other combination, which is consistent with whatever we have proven so far. Whatever we have proven so far does not preclude that possibility. This is a gap which Wigner saw himself, and Wigner plugged this. Wigner's proof actually has a proof why this cannot happen. Why you can't have this and this for two different sets. So I would urge you to read Weinberg, perhaps, if it's possible to get hold of a copy. And I'm not asking you to read the whole bunch of 3 volumes. I'm just asking you to read the Wigner theorem proof from there. And there will be another thing that we will do next, which is essentially from there. That's a theory of symmetry groups acting on the Poincare transformation acting on quantum mechanical states, which is basically at the heart of quantum field theory, or which is at the heart of all kinds of why there are spin-half particles or why there are other kinds of particles in the world. So we will, the basic idea behind this is to understand what kind of operators can you really have acting on your spaces. So if you're going to describe symmetry transformations, you have to do them via either unitary or anti-unitary operators. We will focus on unitary operators for the time being. Anti-unitary operators will come in only in a special case later, maybe, if we get the time. But of course, we won't have the time in the semester, but maybe later. For time reversal. That is the only case where you really need an anti-unitary operator. Okay. So are there any questions before we can wrap up? If none, we are going to stop today.